All right, so the last time we left, what we have is we've got the aluminum losing electrons, really better specifically, the copper ions that are inside this solution, the copper ions gaining the electrons, 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 and those electrons are going into the copper, and we're removing the copper ions. So those copper ions are being removed from the system, and what's happening is they're being deposited right there onto my cathode. Now, over here, and I didn't tell you the name of this, over here, where the oxidation is taking place, this is the anode. This is the anode, so it's an electrode, but it's an anode. And the way to remember that, once again, is this is where oxidation is taking place. And the cute little mnemonic for that is an ox. I like that, the animal, an ox, and a red cat. The anode, we have the electrons being taken from the aluminum going from an aluminum 0 to aluminum +3, and these 3 electrons are going down the wire. So what we're building up on this side, I'm just gonna erase all this. So we're building up on this side is we're building up a bunch of positive charges. Now, remember we do have some negatives in here from the original amount that was in there. Over here, what we have is we've lost the positive charges, but we still have the negatives that were in here at the very beginning. Well, this becomes a problem. All right, so remember what the situation is. We have the law of electrostatic attractions and repulsions. We have the copper +2 ions pulling the electrons this way. So negative charges being pulled by positive charges inside the solution. Okay, well there's a problem. As the reaction goes on, these positive charges are dwindling in value, and so the negative charge is actually increasing in value. That's going to cause a decrease in the electrons coming this way, not only because the positive charges are going down, but because the negative repulsive charges are going up. And then on the other side, over here, we're getting a greater and greater positive charge buildup inside that solution there. And so what do we have? We have ourselves the pooling of electrons this way. So you have yourself your cute little animal, cute little light, whatever it is. My mom had a Elvis little bear. I think it's a bear. No, it's a talking dog, little Elvis dog. And he used to sit there, and when brand new batteries were in, it would be like, love me tender, love me true, all my dreams fulfill. Well, my kids love to press the little foot all the time. They'd go to my mom's house, and all we would hear for hours on end is Connor or Nolan walk around, love me tender, love me true, all my dreams fulfill. And they just keep going. Well, what would happen is that as they kept spending that energy, they ended up reducing the reduction potential of the cathode and increasing the positive pullback on the anode side. And so eventually, a couple days later, or 5 visits later at my mom's house, the little bear, little robot little guy, and it would die. We've all experienced it before. We've seen batteries go down, with flashlights get dimmer. We know when batteries are there. You have your little remote control. It doesn't turn the TV. It drives us crazy. So what's actually happening is that we're removing this negative or positive charge in here, pulling it this way. A rechargeable battery is going to be able to reset this. It's going to be able to go ahead and put more positive charge back in and reverse this. Now, how does it do it? We talked about thermodynamics last time. You're going to put energy in. This is actually spontaneous. This has a negative delta G. So this is actually spontaneously doing a reaction. I didn't have to do anything to make my copper and aluminum react. But we'll talk about the rechargeable batteries later. But here's another thing to remember. The instant this reaction begins, the positive charges will go down, the negative charges will build up, the positive charges will go up, negative charges in relation will go down. And so our battery, we want it to have a certain amount of life. We don't want it to, in the moment we put it in, begin to get weaker and weaker and weaker and weaker. So what we put into it is we put in a salt bridge. This right here is what we're going to call a salt bridge. It's literally what it says it is. It's a bridge of a gel-like salt. What's in there? It doesn't matter. What's in there could be sodium ions and chlorine ions. It's going to be some type of positive and negative ion inside of this bridge, inside of a gel-like substance. And it's big, giant gel-like substance, dissociated positive and negative charges. What's going to happen? Well, as this reaction goes on and as these positive charges build up, the negative ions, the anions inside of the salt bridge will begin to migrate into this solution. Oh, what does that do? Well, as the positive charges build up, these negative charges can also build up, so this side does not become a net positive charge. Ooh, anions go to the anode. Woohoo! What happens over here? As the negative charges, the net negative charges build up over here. We're not adding negative charges, we're just taking away positives. So imagine if I had 100 positives and 100 negatives, we'd say the solution is neutral. But now imagine if all of a sudden after a while I have 20 positives and 100 negatives, we say the solution is now negative. And it changed the negatives, I just took away the positives. Well, these positive charges will move over here and woohoo! We now have ourselves a mitigation, a removal of that buildup, that instantaneous buildup of a positive and negative charge. And so what happens is the voltage is going to stay good for a while. It's not going to instantly go down. Now it still will go down. Those copper ions are going to start going out of the solution there. So we don't want that. And someone might say, well, why not just have the copper ions inside here? Well, we don't want those copper ions migrating this way before the reaction happens either. So the voltage stays the same. So that's the point of the salt bridge. It's not really anything big. It's not really a big deal. Inside of some of your dry cell batteries, that salt bridge is actually, if you see batteries that have a top and bottom, it's actually right there. The wire is actually the casing of the battery. It's not really a big deal. But that's what the salt bridge is. So that salt bridge will actually remove that build up a positive negative instantaneous so that the battery works. So what happens? The electrons flow down to the copper ions. The cathode builds up in size. The anode decreases in size. We would have a buildup of positive charges that could affect the voltage, the pool. We would have a buildup, a removal of positive charges, thus a bigger negative charge build up here, which will reduce the pool. Negatives and negatives repulse. And so we put a salt bridge in where the anions get pulled to the positive side, the cations go to the negative side, and that takes away that instantaneous buildup of net charge. So now we have a flow of electrons, which are now able to power up a load. Whether it's a light bulb or a battery, a radio or an LED, where you're able to make photons at higher energy state, lower energy state, removing photons of energy, all these type things. This is how a galvanic, Italian feller, a galvanic cell is made, or we could say this is an electrolytic cell. I'm sorry, not electrolytic cell, my bad, that's later. A voltaic cell. A voltaic cell. So a galvanic cell or a voltaic cell. This is a basic battery.